Morning, friends.
Hey, good morning.
Morning.
And
Good morning.
three really good people. And Alyssa, good morning, Alyssa. Share a screen and get going. Wasn't that a cool spot we left off yesterday? I just want to stare at that again. Look at that glorious curve. Coffee. Let's see. Let's move you guys over there.
So you mentioned we're doing derivatives and integrals today.
Yes.
So I'm guessing that's just finding the rates of change along each part of curves like that, except this time there's a z dimension.
That's exactly right. So the good thing is mathematically, this is a cakewalk because you already know how to take a derivative. So you really don't have to learn anything new today. But the visual behind this is the part that I think will just tickle you. It will tickle your soul. So we're really looking at calculus in 3D today. And yeah, just derivatives and integrals. And so let's take a look at this. I'm interested if you, here we go again. Screen's blacking out. So I'm figuring out what's causing that. I'm interested to know if you, we'll call this the warm-up, if you understand what is meant by this statement. If I say the sine of t and, I can't read my own writing, what does that even say? 1/4, there we go. 1/4 t squared and cosine of 2t. But notice what I'm going to do next, in the sense that I'm going to say boom, 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 boom. Does that speak to you from yesterday's discussion? I mean, you understand what that's referring to, given that I called R now, R for radius, given that I called it a vector and even used kind of the vector notation. Do you understand the difference to what just happened right there?
Yeah, that's going to be the vector along the line. It's going to like point and move and spiral around probably.
Yeah, and kind of the, you know, the difference between, say, this are those different? And the answer to that is not automatic or obvious at all. So the second one is just telling you sort of almost like three separate formulas. Really, like this is x as a function of t. That's like some function of t, in this case sine. This is y, which is found with some function of t. In this case, it's like a parabola. I take t and square it, and then back to trig again to get z. Z is also a function of t. And so this is a parametric equation, but it's describing how to find all the ordered pairs. Does that make sense? As you march through t. And again, as I've said, t is a great choice, just conceptually, because if you think of t as time marching from 0 on forward, then this is just a pattern as to what the points would be, the ordered pairs would be. So this is just a parametric equation. Parametrically defined equation. But what's the top? Because really the top is what we studied yesterday, which is like a vector. I don't even necessarily like the language. It's like a vector valued function. And I showed you this a little bit in thanks to GeoGebra yesterday, where it was like an arrow. I mean, literally an arrow vector that pointed at the point. Both of these are describing ordered pairs in a sense. It's just that the top one, you're actually literally having a vector starting with its tail at 0, 0 and literally pointing at the point, if you will. And so in a practical sense, I'd say there's no difference at all in terms of how they function. If you think of these problems as just being parametrically defined graphs, there really is no difference. But there is a difference in terms of kind of the arrow pointing at it. And then also with respect to kind of how you conceptualize what we're doing today, kind of the proofiness of this depends a little bit more on thinking of it as a bunch of vectors pointing at it. But practically speaking, either one of them just produces a path in 3D through space. And we saw some neat ones yesterday. And of course, we're thinking, I wonder what this one looks like as well. And notice, if you will, it's not as easy to figure out what this one is doing. And I wouldn't say that's super important, but I will say this. I think the simplest of these three coordinates is the parabola. Do you agree with that? Whereas the other two are trig. And now if it had just been sine and cosine, you might have looked at the first and the third and said, hey, sine of t, cosine of t, that's going to create a circle, which means, and notice that's the x and the z, which means if we looked at the x-z axis as though it was flat, then we would see that circle, and then the parabola would be kind of the spiraling part of it. It would like spiral away from there. So I do want you to think about that a little bit. Let's quickly go into Desmos just to give you a little bit of chance to grow your intuition, as I'm always trying to do. So if I say sine, it's hard to see for some reason. If I say the sine of t, took me like 10 seconds to find the t, and then the cosine of t, except for we said it was 2t. So cumbersome in this app. And notice, as I mentioned yesterday, that kind of just sets it up to go from 0 to 1. As I've shown you before, one of the things that's particularly cool here is to kind of say, let's go from 0 to a, in which case it wants a to be a slider. And so I can actually kind of grow this thing. So notice I didn't think about this before, but notice as soon as it gets to 0, do you notice it actually started at the point 0, 1? Like, could we have figured that out ourselves? In other words, t is 0, so we got the sine of 0 and the cosine of 0. Oh yeah, sine of 0 is 0, cosine of 0 is 1. That would start at the point 0, 1. So as time, or in this case, angle grows, notice it actually kind of, well, interestingly, that kind of was yesterday's problem, wasn't it? So it's like a parabola. So again, that isn't obvious. I frankly was not thinking too deeply about this, and I was thinking, I think that's an ellipse in a polar, and it wasn't. It's yesterday's parabola. And so then what? And do you notice that I'm actually looking at, well, the x and the z axis? So if I consider x to be x, but then the vertical one is actually z, so it's actually y that's going toward us. And so since y is squared, does it make sense it's going to take that shape right there and it's going to, well, grow toward us? It isn't just going to go back and forth on this axis. It's going to kind of grow toward us, I guess you could say, but faster, since it's not just t. So you can you can actually conceptualize what these are going to look like a little bit. As I said, I don't know if that's huge in importance, but it's just kind of cool that you can do it. Let's see, do I need you to be able to see this? I always hate to not have this stuff in the notes. It's a little harder to type in on this app, but I think I'm going to do it anyway. And so that it will be in the notes. So I'll call this R, except for I can't say R of T in this. It doesn't like that, we've noticed. But then if I type the whole thing, I guess the question is, do you have a sense of what this is going to look like now? Maybe that you wouldn't have had I not done what I just did. So let's find out if this agrees with you. So sine of T. And then we had 1/4 T squared. Get out of there, T and square it. Then get out of there, and then it was cosine of 2T. 2. Bam. So notice it tells me it's going from T equals 0 to something. I'm trying to expand. It seems like it never likes you to. Can never figure out how to grab that. This is another place where doing this in this app sort of stinks. Maybe I could just go up here and type it. Here we go again. I get my screen back. There it is. It's on the bottom. You got to pay attention. I may have to switch over and do this on my computer because this is just too tedious. Well, anyway, I guess I'll just have to leave it at that for now. So what I'm going to do is turn it. I'm going to turn it the way that it was just a second ago so that I'm looking at the x-axis and the z-axis. If I can. There we go. Notice that that's the parabola we just saw. So the two that were the most confusing, notice I took the two components, which in this case were x and z, and I thought, wow, that's confusing, that's trig. And so if I knew my stuff, if I practiced, if I memorized, I could say, yeah, that's a parabola. But then it's going to be growing because it doesn't just stay on the x-z axis. The y is causing it to actually grow. And so the fact that it's springing away from us or climbing away from us, if I turn it this way, gosh, this just does not work great. Can you kind of see, yeah, that's a parabola, except for it's sprung along the y-axis? Is there some sense of like, oh yeah, I guess you kind of could see this a little bit. Again, I don't know if that's super important, but notice this is a really cool graph. It's kind of a really beautiful path, if you will. However you choose to look at it. Again, I love the dotted stuff, don't you? Do you see how like I get underneath it and then it turns solid because I can actually see it? Whereas, you know, chunks of that are, if you will, underground. And so notice they show dotted because they dip below the ground. And so, I mean, this is a wonderful visualization. But what I'd like to do now is start doing some calculus on this thing. And it turns out, we'll bring that back over later on maybe, but it turns out the derivative of this is really simple. So if I said, let's go find R prime, and I'll even leave all the vector knowledge into this. Really what you're finding is kind of dr dt. I mean, R is your kind of your y and t is your variable, right? So you're finding dr dt, how R is changing with respect to, again, I'm saying time, but it isn't really time. What is that? Well, fortunately, you just get to take each derivative. In other words, each one individually. So the derivative of the sine of t is the cosine of t. This is what I meant about you don't need to know anything new. The derivative of t squared, power rule. The 2 comes down front, now it becomes 2/4. And the t squared reduces by 1, so now it's t to the 1. And then the cosine of junk, chain rule. What's the derivative of cosine of junk, no matter what the junk is?
It's going to be 2 sine.
Yeah, it's negative sine of the junk unchanged, but chain rule says now times the derivative of the junk. And so Raymond's exactly right. There's a 2 that pops out there. So there I just took the derivative. Now remember, derivative always kind of meant slope, right? Except for remember what you found here is a vector. That's what's kind of interesting. It's not a number. You're used to, plugging in a value for t. So let's actually go do that just for the heck of it. If I say, all right, let's do this at 1, just because 1 seems like a simple number. Thanks to trig, though, this isn't, going to come out very nice. I'll just round this off. So if I say, what's the cosine of 1 radian? I wonder if you can estimate that. I must be in degree mode because I got 1 for the answer to that. Mode, let's go radian mode. Cosine of 1 is 0.54. I guess I'm going to round it to 2 places. Then if I put 1 in for t, I don't need a calculator for that. I guess I better stick with decimals since I did all the rest of them that way. That's 0.5. And then the sine of 1, which becomes the sine of 2. The sine of 2 is 0.9, but then I multiply that by -2, and it sort of turns into -1.82. I mean, you notice that's kind of weird? Like, aren't you used to a derivative telling you a slope? But this isn't a slope. It's actually a vector. Isn't that kind of weird? So like, what does that mean? Or like, what does it tell us? I want to say it's slope, but I just think, huh? So I think I'm going to have to do this with my computer, so I'm going to stop sharing this and we're going to share another screen and I'm going to bring up. Didn't realize I could do that. Oops, that's not what we want. We want GeoGebra. So you're seeing my GeoGebra screen, I think.
Yeah, I can see GeoGebra.
Thank you. Okay, so let's just quickly go back in and type that mess in, except for this time I'm going to have a little more control over the things I want to have control over. And also I can type the dumb thing a whole lot faster. I don't have to go hunting for all the dumb variables everywhere. So this is what I was trying to do, is grab this and expand it. So notice it, and as I mentioned yesterday, it automatically threw in that the variable here, the parameter is t, and then it's going from 0 to 2 pi. Notice I didn't control that. It's kind of cool that they just said, oh, it's trig. You must want to go from 0 to 2 pi. Well, I'm actually going to mess with that a little bit just to kind of show you something neat. But take a look at that. Notice if you kind of go back, this is a pretty interesting shape. Again, it hasn't changed. It's still kind of a parabola from the XZ plane, but then it kind of just grows away from there. But again, I don't really have a super good sense. I don't know if you do, about kind of where that grows. And so let's do something kind of fun here and say we're gonna make a point up. I'll call it, let's see here. I'll call it A. I want to have a point on the graph so that I can just kind of watch it move. And so I'm going to do the same thing I did the other day. Let's see, I need a variable, don't I? So I think before I do this, I'm going to say A. So A is going to be my slider. And then I'll say, now I'm going to make a point. So it's the same exact thing. It's just that I'm going to call this point capital A. And I'm going to say not the sign of T, but the sign of A. I'm very interested that you see the difference. Remember, I said this before, but remember T is everything. That's why you get a graph with 1,000,000 points. Whereas A is not a variable, A is a constant. And right now A is 1. As a matter of fact, that's the point we're interested in the slope in, right? So A is 1 right now. So I'm going to get just a single point, not a ton of points, even though this is the same exact expression. I'm interested that you kind of say, yeah, that makes sense to me. So A squared and then sine of 2 cosine, so much faster, 2A. Bam, so there's a point. And so, and the other thing I want to do is, well, to start with, I'm going to set this thing to work from 0 to 2 pi so I can just kind of watch the direction it's going. I want to watch it grow from 0 to 2 pi. I think that just did it. So now if I look at it in 3D, we saw this a minute ago, because remember how when I had it turned sideways, it started at what we were calling 0, 1, but that's because we had it turned this way, right? But now that I've got it sitting here at 3D, notice as it works its way from 0 to 2 pi, it's kind of flying, well, up in the air, like along the y-axis. And so it kind of goes over there. And then it just kind of keeps going. And notice if I zoomed out, you could see the path, but it just keeps on going. So that's kind of fun. Well, let's take it back to the point 1. So I'm right there. That's where I am. I'm like underground. And can you appreciate that the slope in 3D is a really complicated thing? Like, what would you conceptualize? I mean, let's just stare at that point for a minute as I kind of rotate this around. Let's just pretend you're hiking on this trail. First of all, are you hiking uphill or downhill? Does it make sense that makes a difference? Is the slope here steep positively or steep negatively? And in terms of hiking, it doesn't make any difference, because if you'd said, well, I don't know about you, but the slope to me looks really steep, like maybe 6, I don't know, rise of 6 and run of 1, something like that. It's steep enough though that you could miss that by a mile, but the slope is 6, and you know, sort of doesn't matter which way you're going. If you're going up, it'd be +6. If you're going down, it'd be -6. But you know, part of me wants to think in the real world, it's like, well, this is absolute value of 6. It's absolute value. I don't really care what the sign is. It's just that's how steep it is. But you know, I find myself thinking about the answer we just got, and I'm like, what does that even mean? What does that have to do with anything? Why is it a vector? How come I didn't get the answer 6? Like, don't we want the answer 6 if that's really the slope? What in the world does that vector actually mean? Any thoughts on that? Like, why? And I'm gonna graph it in just a second and see if you can connect it, but
Isn't it just the direction that you're traveling at that point, and then how fast you're going down the X, Y, and Z axis?
so why is it given as a vector? Like, it just feels like it should be, well, again, what mathematicians call a scalar. Doesn't it feel like it should just be? And so you're talking about speed, and you're right about that, because we're going to get into that. That's one of the things a derivative conceptualizes that's really wonderful is acceleration, velocity, and position. So I'm in that position over there, whereas if I'm kind of over here, notice if I'm up there, doesn't it feel like, okay, well here, again, I'm thinking of this as a hike on a path through, you know, maybe think of it as a roller coaster, because you could actually, you know, get a roller coaster to be shaped like this. That doesn't feel as steep, right? But if I plugged in the point, notice it's almost 3. So we'll go do 3 in just a second. But if I plug 3 in, I sort of expect to get kind of a smaller answer, like maybe 3/4 is the slope or something like that. But again, I'm looking at these vectors. I'm thinking, why is the answer a vector? And I'm just hoping to make sure you feel the tension of this before I answer it.
Well, I guess you can think of like the slope as like a unit, I guess, like 3/4. So it'd be, 3 meters every 4 minutes or whatever. And it should, because a vector doesn't have time, like Cheyenne was saying. It's like how fast you're going somewhere. A vector, oh shoot, it doesn't have, sorry, direction. So we have a direction, don't we? Because we're going a specific direction on this thing, on this path.
That's an important point. So let's take a look at that for a second. Do you agree that, so I'm at sort of time 3 right now in the roller coaster, and I'm over here, and I'll zoom out a little bit so you can see a little bit more of it. But it's like, you might say the slope there is 3/4. It looks pretty low, doesn't it? But does it make sense it actually has a direction? I mean, look at this from the air. I mean, aren't you traveling in that direction? You see what I'm saying? It's like, it's not enough anymore just to say what the slope is. That's kind of the problem in 3D. Like back in the days when you had a line, if you said the slope was 3/4, there was no question about what that meant, because a line is in 2 dimensions and you're going that way. And the 3 and the 4 told everything that you needed to know. Does that make sense? Whereas here, notice over here, you're actually kind of heading well off in that direction. Whereas when we went back to 1, notice here, you're actually heading, well, either this way or heading that way. Do you see how there's like a directional component that's lost? And that's kind of why the vector thing is so cool. That's why in the end, this is a vector valued function, not just kind of the 3 ordered, like an ordered triple. Because we need the slope. Yeah, I want to know the slope. I want to know how steep it is that I'm hiking on right there, but I also kind of want to know what direction I'm going. So let's throw that vector in there that we just got a minute ago. Evaluated at 1. And I'm sitting at the point t = 1 right now. But we got the vector, so I'll call it V for vector. And we got 0.54, I'm obviously rounding this off, and 0.5 and -1.82. And notice where it draws it, because I didn't say otherwise. It draws it from 0, 0. So it's actually not where it belongs. But I want you to stare at that vector a little bit, and I'll color it some other color just so it helps you see this the best you can. I love green. That's a crazy green color. Except for it didn't really turn that green. It's one thing I've noticed about this, really feels weird. It's like I want it to be kind of a light color. Let's try orange. If that doesn't work, I'm going to give up. I don't like that at all. But I want you to stare. Let's see if I can get this thing. I want you to stare at that vector. What do you notice about it? Is this the right? Did we get it right? What is that telling us?
It's the same slope as the line right there at that point.
Do you agree with what Raymond said?
Yeah. Is the length also proportional to anything? Is it telling us something on length, or is that just pointing into infinity?
That is just a fabulous question. I'm going to let it hang for a second. Remember before, like the length of the vector was like miles per hour or pounds or something. And so, is the length of that vector mean anything here? Am I going to get the same length vector when we go over to the 0.3?
That is a good question.
It's a wonderful question. So let me do something fun here. I'm going to take that vector and I'm going to move it over to A. And so this is kind of neat. Vector, notice it says start point and end point. Let's see, can I do this yet? Yeah. So here's kind of something tricky I figured out. So what I want to do is I want to go from the start point A, but then I want to go from A and then add my vector V to it. you see how that moved it into the right position? That's kind of fun. This is one of the reasons for vector addition. Notice I can turn the other one off now. Not that one, this one. Oddly, the color of that kind of just suddenly turned to something I like too. Let's make this guy green. Maybe its green will look a little nicer. Let's make it bright green.
I think in the main settings, you can also disable the lighting, and that makes the colors show up a lot nicer.
Did you say disable what?
Lighting, there's a checkbox if you go to the settings. Yeah, up there.
Let's go play with that.
And yeah.
Use lighting. So you think uncheck that? That was something you discovered and it was good?
Yeah, like I'm actually able to use a bright pink now and it shows up.
Oh yeah, yeah, I just did that and it seems to be nicer in green. Do you see what it's telling us? I mean, isn't that cool? This was like Raymond's the first one to say something about it, but notice that is exactly where you're pointing right now. In other words, that is the direct. And by the way, why is it down? How come it wasn't up? Remember how we said it's like, why isn't it?
Because we got that negative Z.
Yeah, but the arrowhead, I mean, that's why it's going down, but why isn't the vector going up? Why wasn't it going from A up? Because that's kind of a direction of travel thing, isn't it? So how do we know which way to go with it? So it went down, but why did it go down?
I assume it's because that's the way the curve is going.
That's exactly right. As time goes by, look at A. A is 1 right now. If I go to A is 2, isn't that the direction you're traveling? So basically in this roller coaster, we already saw this, but we started up here and we were going this direction. So that arrowhead was actually telling us that's the direction you're going right now. So therefore you're experiencing the negative version of this slope. Does that make sense? So that's important. We could have got it to go the other direction, but it would have had to be kind of a negative value. That's kind of interesting. So that vector is telling us something really profound, isn't it? I mean, that's really cool. The fact that it's a vector is actually instrumental. I'm like, what if this had popped out the answer 7 for the slope? That's great, but in this world, you got to say what direction 7 is going. It isn't enough just to say your slope is 7. Although I think you might agree you'd like to know that, right? If you were kind of the designer of this roller coaster, to be able to say, oh, they're going down at 7 right now. I don't really care where they are. They're going down at 7, and you're figuring out how many G's that is, and is the track big enough, and will they pass out, and all those kind of things. It's not. I'd like to know that too. But the fact that that's perfectly tangent to the curve, that's what a derivative always did, isn't it? Like we literally just found the tangent to the curve right there. And so in 3D, it would actually take 3 components to do that. So do you see why a vector is such a powerful way to look at this? Why we just learned recently that a vector valued function, if you think of this function as defined by vectors, literally by an arrow that goes from 0, 0 out to A, even though I don't bother to draw it in there. Why it's so profound to think of this green arrow, this green as a vector. So do you think the length tells us anything?
Well, it's supposed to. I'm just wondering if GeoGebra actually goes that far, because seems pretty intense.
Yeah, it's really intense. I wish I could copy this over so we could draw on it, but that's the disadvantage of what I just did. Trying to get it to share. So is there a way to know the length of that vector that we just found?
You can Pythagorean theorem.
Yeah.
You know how to find magnitude.
Magnitude, exactly.
Thank you. I couldn't think of the word magnitude.
Yeah, I heard you working that over in your mind, but you pulled out exactly what a magnitude is, which is to use Pythagorean theorem on it. So do that. I'm just gonna write down the answer to it. I'm gonna write it as a decimal too, since I already rounded off 0.4 anyway. There's really no sense in giving some answer as though it was exact. You understand the logic in that? 0.5 is the only exact answer in that list. Interestingly, when I take negative 1.82 and square it, though, I'm going to get a positive. So I got 1.96 for this. Which to me is a little disappointing, because when I was looking at the length of that vector, I'm thinking that was a lot longer than that, wasn't it? It's like 2. Thing really length 2. Does it seem like it's length 2? Well, I guess it is. Do you agree with that?
Yeah, it looks like it's 2.
It actually is length 2. And do you think 2 is a reasonable answer for that slope? So is that a slope of 2? Is that what the length of that is telling us? The magnitude of that is actually kind of the numerical answer. Because again, if I'm thinking of this as hiking, right? The fact that I'm hiking up something that's a 2-to-1 slope, it's like, whoo, you know, that number means something, right? Like, wow, man, that's really tiring. Or in this case, if you're going down, whoa, going down something that's a slope of 2, man, I'm really going to be flying if this is a roller coaster. Does that actually look like a slope of 2? Notice how hard that is to tell, because it's how do you look at it correctly? The only way I could look at it correctly is if I was looking at it perpendicularly. But would you agree that actually, I mean, looking at your scale over here, would you agree that's actually what that's telling you? If this height right here is 2, doesn't that right there look like half of that? In other words, this is 2 and this is 1, like that. I think that's what that's telling us. Do you agree with that? So the vector is cool because it's actually telling you everything. If I just told you the slope is 2, you would be losing the information about what direction that's actually traveling right now. You know, what direction is the roller coaster heading? But when you have the vector version of it, anytime you want to actually know the scalar answer to the slope, not the vector answer for the slope, but the vector contains that. Does that make sense? The vector just contains more information. So it's kind of a better way to look at it. So let's see if that's true, then what's going to happen if I let time go forward, and what's going to happen to the arrow if I kind of let time go forward and I kind of go down to the bottom here, like the bottom of the roller coaster? What's going to happen to the length of the arrow when I get down here just before the curve?
It should shrink a lot.
That's my thinking too, because isn't that slope down there a lot shorter? So let's see, I think I can go in here to settings and slider. Seemed like there was a way to control, because I'm going to animate it here in a second. And I think I could control how fast it animates, but I just can't remember where. Basic, color, position, advanced. I guess not.
I think it was that increment.
You think you saw it?
Well, it just says increment and it's got nothing in there. So maybe if you did increments of 0.5 or 0.1 and then you just automate it using the play button,
Yeah.
or the speed there. Yeah,
You're right. Yeah, right below increment is speed. So I don't know what my lowest speed is, but I'd like this to go really slow. I have this vague memory that it was like 0.05 is the slowest you could go. Let's see if it let that happen. Go back and look at it again. Yeah, it's stuck at 0.05. So now if I animate it, let's take it all the way back to 0. Let me think for a second. Let's do something a little fancier here real quick. So this vector v that I just typed in a minute ago, like that was specific to 1. Do you agree with that? Like that only worked at t is 1. But let's go try to do a little better than that. Let's go delete that. What just got deleted with that? Something got deleted. Oh, that vector that I typed. So this time I'm going to go say v equals, But I'm going to do something a little more creative this time and say, well, what was our derivative? Wasn't it the derivative of sine of t was cosine of t? And the derivative of 1/4 t squared was 1/2 t. Except for what I'm going to do instead of putting t in here is put a in here so that I can actually evaluate this vector and have it be, well, every answer. Isn't that kind of cool? So this is going to be the same vector it was a minute ago. In other words, when this was 1, I'm going to go back and put 1 in there just so we can see if it actually works. Uh-oh, I got out of this. Is it going to let me get back in it and edit it? Yeah, I think it's not liking that. Now that I already typed it, it's kind of getting all picky. I think it's hating me, so I'm just going to start over. Doesn't seem very editable sometimes. So sine of a 1/2 times t, but we're using a, and then we said -2 times the sine of 2a. Ding, ding. So do you see that that's working? Like, isn't that the answer? I'm hoping it is. No, it actually isn't the answer, is it? Did I type something wrong in my calculator earlier? Cosine of 1. Oh no, I'm just dumb. Why'd you guys let me do that? The derivative of sine is cosine. That's why you check your work. Hopefully it'll let me edit this. Notice it's not liking it. It does not want to let me edit it. I'm kind of thinking, great, am I gonna have to type this whole stupid thing again? There we go. So now it's working, right? So derivative of sine is cosine. Derivative of 1/2 t squared is 1/2 t. Derivative of cosine of 2t is negative sine of, so this is working now. And then I went on and said, okay, let's make a vector from that starts from a and then it goes to a plus v. Right?
So you can also go into settings and on this top one, if you want to, and change the position of that to a, like on the v vector.
Let's describe that one more time.
If you click on the 3 dots for the v vector that we just the second from the bottom, and click on settings for that, you can go to, oh, okay, I guess it's not there. Never mind. I thought sometimes it has position there, and then you could just change that to the position of
Yeah.
That makes it easier.
I actually think you can do what you just said. In other words, I sort of did it manually, and you're basically saying there's a way you can actually position the original vector v. So I kind of made the vector v, but then I repositioned it. Ben's basically saying, and I actually think you're right, Ben, there's a way you can do that. So then you click on vector v and then reposition it to the other location. So now even the vector is slidable, right? So if I go back to 0, and I actually want you to predict, what am I going to see when I go back to time 0? Do you remember where that was? That was right up here, correct? So think about this. Don't say it out loud, but think about this. Just there I am. I'm up there at the point x is 0, z is 1. That's where I am right now. And so what's going to happen when I go there? So you shouldn't be surprised that's pointing to the right. However, I'm a little surprised personally that its length is 1, because what's the slope up there?
It should be 0.
Yeah, it should be 0, shouldn't it?
I was wondering how I was gonna animate that as well.
I was expecting not to see anything, frankly, because I was expecting to see a vector that was horizontal of length 0. Therefore, I wouldn't see anything. So I was going to say, well, where is it? And see what you guys thought. So I'm a little troubled by that. Let's leave that for a second and think about it. But so notice it's animated really slow. So think about this as a roller coaster. It's like you're going down the hill. Notice your slope is increasing, increasing, increasing. But notice the whole time that thing is staying perfectly tangent to the curve. It's just really cool. Wow. That's really cool that you can get it to go that slow. I know you can't do that in Desmos. Thing that if it doesn't animate slowly, then it's really hard to kind of see what's going on. Of course, I can kind of spin this around so we can watch it, and it's still, so notice the vector is going to get shorter and shorter and shorter. But based on what we just learned a second ago, I don't think it's going to go to length 0. I think it's probably going to go to length 1 again, isn't it? So that's bothering me a little bit, but boom, right there was horizontal. But the cool way to think about this is it's kind of like the headlights on the roller coaster. Like this is the direction the headlights are facing at any time. Or in terms of velocity, for those of you who've taken physics, like this is the direction that thing is heading at any given point in time. Notice how steep the vector is now, man. You're really climbing. So that's pretty powerful, isn't it? Like what the derivative produces.
Makes me amazed we don't have to sign a waiver every time we enter a theme park.
No kidding. You're hoping that somebody did their math. That's the issue. I don't know about you, but did you notice just a second ago when it got to the peak up there? Actually, I genuinely don't know the answer to this question. And there's probably a command in here for magnitude, but again, I'm finding myself looking at that thinking, isn't the slope there kind of back to 0 again? I'm not exactly at the peak because I just kind of estimated it. By the way, where do you think that peak is? Take a look at what A is right now. What's the actual peak?
Probably pi.
Probably pi, because notice I'm a hair short of it. And so 3.1 isn't quite big enough. And so probably if I actually got to the peak, I would be at pi. And I didn't look to see where we were down here, but I have a feeling that that point was pi over 2, because I remember 1 was up here, so 1.57. I think that valley right there was 1.57. Now we're at 3.14. So I think I could go here. I guess it isn't worth doing anyway. But notice that length, that vector length, and you can see right here, just looking at the vector, that's not 0. So that's kind of troubling, isn't it?
Well, I don't know about that one, but when we started, I realized that if we're at a slope of 0, we have cosine of A, right? So if it's cosine of 0, that's 1 right there.
Yeah, in other words, you're recognizing what's causing.
Yeah, okay, and then sine of 0. Yeah, so it would make sense that it would just be 1, but the other one doesn't make sense to me.
Yeah, let's go to,
Because if it's at that peak, it should be 1 too, essentially.
exactly. So we have a mystery here. Don't you want the answer to that to be 0? And notice like before, you can recognize these answers here, because what's the cosine of pi? Well, isn't the cosine of pi -1? And then you have 1/2 of pi. Yeah, that makes sense. That'd be 1.57. And then sine of, well, wait a second. Notice it's not pi, it's 2 pi, but the sine of 2 pi is the y coordinate of 2 pi, which is actually 0. So that actually makes sense that this would be the vector, if you will.
So if we're at 0 on the xy plane, do we still have to count 1 on the z plane? So wouldn't it be -2 sine of 2?
Yes, except for it's 2 pi, because we're saying A is pi. So it's -2 sine of 2 pi. But the sine of 2 pi is 0. Therefore, when you multiply by 2, it doesn't change it. It's still 0. Is that the question you asked?
Yeah, I'm just trying to think of slope in a 3D. And so I was wondering, since we're up
Yeah.
in the z direction 1, I wondered kind of if that, I'm trying to explain why it would be so big, the magnitude.
Yeah. So I'm thinking, I'm not happy, but I'm thinking about, what's the meaning of that? I thought I had that figured out. I thought slope was, because there's places where that looks correct, if you will, but anyway, you can see how, why the answer to this is a vector. I think that's really profound and powerful and beautiful. I think that makes all kinds of sense.
So the slope at the top of that, at the crossing, is the same magnitude, almost the same magnitude as when we were on the steepest part back there.
Oh, you did the math on that? Yeah, it's
Yeah, I
weird.
got
Isn't it?
1.86. But if I've been thinking about this like a roller coaster, I know you told us to think about it as a hike. You would have a lot of momentum and force pulling you in that direction coming off that big. Well, I guess it's the
Mhm.
top of the hill. I don't know. It's hard to.
Yeah, I was kind of going through the same thinking. In other words, can you think of it as like speed? Because if that's speed, and then that is one of the best applications for this is position and speed. And so based on where you are, you're going to be going a different speed. And so that the length of that arrow will be speed. So that does mean something. But apparently I'm wrong, like that isn't slope. It looked like it was working at 1, didn't it?
Yeah, it won it. I was curious on getting some references. I wanted to see kind of what it was at the very bottom of it and what it did, but I can't. It did get smaller at the bottom, didn't it?
Let's go to that. Let's go there because we said we thought that was pi divided by 2, which I think it is. Let's see if it isn't. It isn't pi over 2 at the bottom. I think I just typed pi over 2, but that's not pi over 2. Maybe I fat fingered it. Yep, I did.
Yeah,
fat finger it.
super small.
Yeah, so notice you get a very different answer. Got to stay zoomed out a little bit to.
I wonder if it's the line perpendicular to the tangent to that curve in that spot.
What about it?
I mean, that vector u, I wonder if it's perpendicular to the actual slope vector, if it's not the slope, or are we talking about the magnitude?
I like your idea. You're basically saying if we found if somehow the perpendicular of this vector would be the actual slope. Yeah. Well, let's let that sit for a second. Maybe we'll get to the bottom of that. So just for the sake of kind of a sort of a quick practice problem, something that looks like maybe something that you'd see in your assignment, if I you're back. So if I gave you this expression, 2t minus 3 and t squared minus 12 and square root of t. Notice these are much nicer than trig expressions. Come on, quit doing that. Jeez, what's going on? I think it's a good idea. Let's see, what are you guys seeing right now?
Your note sheet.
You're okay?
I think so.
if I gave you that and then just asked you what is R prime of 4? The only thing you should potentially have a little bit of trouble with from memory is what's the derivative of the square root of t? And then we're going to take it one step further than this. So you should say, okay, that's not a very hard derivative to take. The derivative of 2t minus 3 is 2. The derivative of t squared is 2t. Derivative of constants is nothing, so the 3 and the 12 made no difference. Can you still take the derivative of the square root of t?
It's -1/2 t, right?
Yeah, you should see that it's t to the 1/2. And then power rule would bring the 1/2 down front, and then the t is there, but then it reduces by 1. So 1/2 minus 1 is that. So therefore, that's really the square root of t. But what does the negative do to that? It drops it down on the bottom. So probably a nicer way to write it then would be to write it like that. In terms of plugging numbers in. Notice I was nice to you and asked you for, what's the answer to this at 4? Because you had to take a square root. So that's going to make this come out a little easier. So there's our general derivative equation. So of course, this isn't very painful. Notice that first one is interesting because it's just always 2, like it isn't even dependent on t. It's just 2 every time, doesn't make any difference. It's 2 every single time. That's kind of interesting. But then of course, 2 times 4 is 8. The square root of 4 is 2. 2 times 2 is 4. So that's kind of your slope vector. So one of the questions you asked in your assignment, which isn't a huge leap above this, but I just want to see if you can survive this. Could you actually find the equation for the line tangent to So it's kind of the same question, but remember lines are really weird in this world. And we just saw a second ago that we got a vector answer for this, but remember that vector R prime, should put the prime back in here. That vector R prime of 4 is nowhere in particular. Remember, it's like it's just anywhere. And we moved it to kind of where it belongs in the GeoGebra, but it's not at 0, 0. I mean, I guess you could say it is at 0, 0 right now. So how do you find from a couple of days ago the equation of the line, the entire line tangent to the curve, not just kind of the vector itself, but the entire line? So we did a bunch of that back in the day in Calc 1. We said, find the equation of the line tangent to the curve at some point. Well, we're doing the same thing here. It's just the curve is now a 3D curve. Did you practice finding the equation of a line in 3D enough that you can do this? So you should say, if you remember this, that you need a point. In other words, the point tells you where the line is. That's the only 2 things you need. It's the 2 things you've ever needed. Back in the day in Math 60 or in just regular Algebra 1, you said, I need a point and I need a slope. If I have a point, and then I can count rise over run, then I can draw a line. Well, the same thing is true here. You need a point and you need the direction that the line goes from there. So you have the direction the line goes from there. That's R prime of 4. That's your direction vector. That's what we just saw on the graph a second ago. What you don't have is a point. In other words, you're going to have to go back and actually figure out what R, not R prime, but R of 4 is. In other words, where are you? What point are you actually at? Well, that's not hard. And notice that's a point. It's not a vector, it's a point. Well, it could be thought of as a vector. It's just, the point is got a vector coming from 0, 0. So again, I find myself thinking, do I write a vector symbol here? Do I write a bracket? I mean, it sort of doesn't matter. But if I put 4 in, 2 times 4 is 8, 8 minus 3 is 5. I get 5 for the x coordinate. 4 squared is 16 minus 12 is 4. And the square root of 4 is 2. And so that's the point I'm at in space right now, which is what we had graphed a minute ago. That's what I was calling capital A. That's where you are. That's where you are right now. You're at the point 542 on the graph, conceptualized as an ordered triple or a vector emanating from 0, 0, 0 to the point 542. If you want to think of this as a bracket, as a kind of a vector. So now the line is easy. Yes, you agree with that? Well, if you understand how lines look in this world, the tangent line, remember there's 2 ways to do it. I'll write them both here just because maybe this is now that we're applying it to something. So you would say either the point 542, and then you add to that t or any other letter multiplied by the vector 2, 8, 1/4. And again, I'm very interested that you're able to visualize that in the sense that you say, okay, well, all this is a description of how to get points. You take the point 542, and then you say, okay, first of all, t is going to be 0. Okay, so that would mean 542 plus 0, 0, 0. So that's the point 542. But then you make t 0.1. So now you have 0.2 and 0.8 and 0.25. Let's see, 0.025. And so you add that to 542, and now you get another point, and that point's going to be right next to the previous one. Do you see this as a point finding equation? Do you see why this is working, I guess? Don't just do this because, the teacher said to write it that way. Put the point and then put the vector. I just wrote it that way and they said I got it right. Visualize that that's actually working. You can pick t to be not just what you want, but every single number possible, every real number. Negative 0.2, negative 3.6. T is 7, T is 7.125, and that's going to create a bunch of points. If you pick T to be negative, then the points are going to kind of go backwards, right? From where the vector wanted to point, it's going to go the other direction. It's going to go behind you. If T is positive, it's going to go in front of you. I'm interested that you can kind of see that. So we also said that this would be the same way of writing it. Your x coordinate is found by going 5 plus 2t, right? Isn't that what your x's are? 5 and 2t. And then I look at the y's and there's a 4 and an 8. So it'd be 4 plus 8 multiplied by t. And your z's are 2 plus 1/4 multiplied by t. We said those are identical. That's 2 ways of writing it. I don't know about you, but I like that one better. It sort of feels better to me because I just think of it as like a parametric ordered pair. That's what we've been playing with lately. And so I think in the interest of time, I won't graph this because I want to show you another problem, but it'd be good to go in there and stick that all into GeoGebra, wouldn't it? And then to graph the point 542 and then draw the line 5 plus 2t, 4 plus 8t, 2 plus 1/4 t, and kind of see, is it tangent? Does it really go through the point 542? It's like you don't need anybody to grade this stuff, right? Especially on the next test I give. Stick that into GeoGebra, and as many of you are doing on your test now, brag, that's like, don't even grade this one. I know I got it right. Verified in GeoGebra. I love those notes. Good job. So hopefully I didn't screw up because I'm not checking my work. Now, let me show you something kind of cool as an application. We're going to build on this starting next week, but because the next chapter is actually motion in space. but motion of anything in physics has an acceleration, a velocity, and a position. That's, for some reason, S is always used for position. So we'll build on this, as I said, but there's acceleration, velocity. That's the components that motion actually has. Where are you? How fast are you going? And are you increasing or decreasing your speed? Are you just in cruise control? Like you're never, acceleration is 0. But if you've never thought about it before, like that's the 3 components of motion. So oddly, although you might think I'm sitting still right now, my velocity is 0. Well, yeah, but it depends on your reference frame, because did you know that you are hurtling through space at 66,000 miles an hour right now? Because you live on a ball of dirt called Earth. And we are flying around the sun. Do the math. We're 93 million miles from the sun. What's the circumference of your path then if your radius is 93 million miles? And how long does it take to go around there? 1 year. Turn that into hours. How many hours does it take? How many miles did you fly? You're flying 66,000 miles an hour through space right now. So that's pretty amazing. So this concept of motion, you know, like, what am I doing? Yeah, you're not moving relative to the Earth, but you are moving relative to the sun. Interesting. I digress. So let me actually give you the velocity vector. And notice this time, time actually makes sense as our parameter, but I'm just making this up. This is, you know, in a sense, nonsensical. I'm going to give you a, what's that called? A rational equation for X and a polynomial equation for Y and a trig equation for Z. Isn't that kind of fun? Totally random, totally made up. That's really weird, if you will, that if you were actually in space flying around, that such weird equations would model your flight. But you should appreciate this is going to create some fun path through space that I, you know, find myself wanting to see. But do you remember from our previous discussion that this is how this worked? If you went from position to velocity to acceleration, what were we doing if we were working our way in that direction? What is velocity? Isn't a velocity the change of position over time, like miles per hour? So you're taking a derivative to move in that direction. Remember that discussion? And the change of velocity over time, if your velocity is changing, that's what we define as acceleration. Like these are derivatives, right? So if I gave you a velocity vector and said, hey, what's the acceleration? Then you could take the derivative and find that out. But what is it if you go backwards? What does the fundamental theorem of calculus say if you decide I'd rather go the other direction?
Integrals.
Integrals. Fundamental theorem of calculus says, hey, those are the opposite operation. So if I give you velocity, and let's do this one first. So we'll say question 1, give acceleration. So you already know that one. And notice the answer to that is going to be a vector. But again, it's good review because maybe you'll blow the derivative of 2 over t. That's kind of an intimidating derivative, or one that at least means you still have to know your stuff. You probably have no trouble with the derivative of t cubed or the derivative of sine. But I wonder if you can survive the derivative of 2 over t. And by the way, this velocity vector that I just gave you is kind of like the green vector on the original warm-up problem for this class. I'm actually giving you the the velocity vector, not the original curve. Like we don't have the original curve here. Do you understand that? We don't have a position curve. We can't graph a position. We don't know. That's one of the most interesting parts of this. We don't have that though. We just have something that tells us about our velocity. We have no idea where we're going. We're just cruising along. So 2 over t, of course, is the same as 2 to the t negative 1. And then you take derivatives by multiplying by the power and then decreasing the exponent by 1. So that would go to negative 2. So it'd be negative 2t to the negative 2, or it would kind of be cooler, I think, or look nicer if you wrote it as a positive 2. You agree with that? Is that what you got? So that's not that bad. And again, you probably don't have a super good sense of, what is that? What does it even mean? We should have time to like plug in a number and play with this in just a second. But the harder question to this is, what if I wanted to go this way? Question 2. And of course, I think you could appreciate, and by the way, this is the backbone of, I'll make a quick pitch for what I'm teaching this summer. I'm teaching differential equations this summer. If you look at your program, where you're going and so forth, if you need differential equations at this school, because it's a community college, we can only offer 200 level classes. We can't offer 300 level classes, but this transfers to OIT is, I forgot the number, but it's like 320. I think it's 356. Ours is 256, but it transfers. Our 256 transfers, and you knock out their 356 differential equation requirement. So, if you have time, if it's in your schedule, unbelievably beautiful. Somehow I was allowed a math degree without ever taking differential equations, and it is a beautiful thing. But does it make sense? That's what you have here, is you have an equation with a derivative built into it. In other words, you're really being told here, ds dt. Whoops. In other words, you're given an equation where the only thing you know something about is the derivative. That's a derivative differential, a derivative equation. This equation's got a derivative already built into it. That's the only thing you had access to. It's kind of like, I don't know my position, but I know how fast I'm going. There's a lot of really cool examples of this that I will show you this summer if you join me.
Sweet.
So,
I'm looking forward to it.
yeah, I saw you signed up in there, Raymond. I'm glad you're in there. I saw you in there too, Ben. I forgot who else was in there that's in this class. My failing memory. Were you in there, Connor?
I just signed up yesterday because
Oh, sweet.
they require our instructor, or not our instructors, but like Dusty is my advisor to like open it up for me. So that held me up really hard.
Yeah, technically you have to take this class to be in it, but you don't really have to. So actually, any of you that want to take it, need to take it, whatever. If you don't have the prerequisite for some reason, I mean, you need calculus 1 and 2. You don't actually have to have 3, but there's a couple things we'll do in there that you guys will know that the other people won't. But if you need permission to get in there, I could give you the permission code. You can get in.
I ended up getting it because you were saying that it was threatened to be canceled, and I didn't want to wait a year. So I just told him, I was like, hey man, I need him right now.
Get me in there. Yeah, good.
Oh, it might get canceled. That sucks.
I don't think it will. When I went in there the other day and looked, and there were 8, and that was before Connor got in there. So we try not to cancel those just because they're classes. They're hard for, we only offer them once a year, and if you're in there, you need it. And so, sorry, you'll have to try next year. That isn't really fair. So the problem is if there's like 2, 3, 4, then the school starts to get really, but if you get up to like 8, 9, they'll let it run. So we're good. Yep. We're doing it. I will say is, I'm relatively enthusiastic about what I teach because I just think the stuff is so cool. That is far and away my favorite class ever. It is the applications that are just so beautiful. Anyway, how would the position, which again is given as a vector, how would that work? Given how derivatives worked, how would integrals work? Well, The fundamental theorem of calculus says it's the same exact process, just underivative this original problem back here. And, you know, again, that's, even though it's been one term already, it's kind of like, that's a little fuzzy, isn't it? Like the easiest problem up there is probably the t cubed. And so you do the reverse of what you just did. A second ago, you took the 3 and you brought it down front and decreased this by 2. And so what's the reverse process that wasn't in your mind fresh at one point? It's, well, you raise it 1 power, you take the 3 and add 1 to it, and then you divide by that. That's exactly the reverse process. So that's probably the easiest one. Maybe sine would be the next easiest one. Let's see, the derivative of cosine is negative sine. It's like cosine, right? But the derivative of cosine is negative sine, and we don't want negative sine, we want positive. So then this must be negative, right? Is that right? But what about 2 over t? It's a little rougher. Got a good memory? Remember, 2 over t is really 2t to the negative 1. And according to what we just did with t to the cubed, what do you do to that? Because it's a power rule. You add 1. You add 1 to the exponent, which means it goes to t to the 0. That's fine. That's okay. T to the 0 is 1. But then you divide by 0. You divide by that, right? Do you see that that just exploded? You just touched the 2 wires together and it sparked. Dividing by 0 just made that blow up to infinity, and therefore that's a hint that this is the one weird case. Like that is not what you do here. Who remembers? Some of you remembered before I even gave that little diatribe, but what's the integral of, well, 1 over t?
ln x. Right?
Yeah, that's exactly right. That was that weird case where it was natural log. And again, I'd be willing to bet that lots of you are like, okay, I vaguely remember that now that you reminded me, but it's like, why? Where was that? How did we make that? Where did that come from? What? Why would it be natural log? I get that it broke, but why would it be natural log? The 2 just comes along for the ride. So there's our position equation. Now, what was a little dangerous though about taking integrals? What was kind of the one thing that?
Got to add c.
Yeah, it sort of depends, because when you work backwards, if all you know is your velocity, then where are you? I mean, that's kind of what you're saying, what we're saying here. Where are you? Well, it actually kind of depends on where you started. Does that make sense? It depends on, and we'll make a lot of this in differential equations somewhere. It depends on your initial position. And let me give you an example. Let's say you have a pool, just to keep it something that you're a little bit related to, and you have like chlorine kind of dumping into the pool. Maybe, you know, a drip pops in it once an hour or something like that, because you're just trying to keep it from growing algae. And so you have it popping in at a rate of 1 drip per hour. Well, notice that's a derivative statement. That's a rate. Like, that's all you know. I have chlorine dripping in my pool at 1 drop per hour. And so, but you know, one of the questions a person might ask is, well, how much chlorine is in the pool? You see what I'm saying? Like, what's the position? How much chlorine is actually in the pool? Well, does it make sense? It depends on where you started. How much was in there when you first started dripping it? Was there already a pound in there? Well, you got to know that. You got to know your initial conditions. So what if I added to this problem an initial position? And of course, that would be S of 0. Initial is kind of code for time equals 0, right? Like normally, if you, and no, time equals 0 is not like, you know, before Christ, after Christ, 2,000 years ago. It's when you started. In other words, hey, I just started putting chlorine in my pool because I saw it was green. And so time 0 is like now, because you just started doing it. So what if I just randomly gave you, and I'll write the word given here just so you don't think we figured this out, but I'll just make up some quick numbers here, like 2, 3, 5. That's where you actually started. That's where you were when you started. That was known.
Is that a vector or a point?
It's a good question. It's a vector, but again, it's a point. And the only reason we call it a vector is because we say it emanated from 0, 0 up to there. In other words, that's how we're describing the point. But yeah, I feel like it's interchangeable. In other words, it could just as easily think of that as a point and be just fine. That's why at the start of this class, I was saying, does it make any difference? You know, is this thing a parametric point with parentheses around it? Or is it a vector? And it's kind of like, yeah, it's both. It's either one.
So if you use that with the velocity equation, isn't that your equation for, I guess, the drips, if that's how we're thinking of it?
Say that one more time.
I'm just trying to think, like we were talking about a 3D equation of a line. If that is our initial given point, and then we add t times v, isn't that kind of our location, I guess?
Yeah, that's exactly how you think about this. I'm gonna double check your.
Well, I just wonder because then we wouldn't need to take the integral, so I'm kind of confused on where that fits in.
Well, let's think about this a second. Let me write this down and we'll talk about that. So really, I should be saying that the answer to this is really 2 natural log of t plus kind of a, I guess I'll say constant 1, and then 1/4 t to the 4th plus some other constant 2, and then negative cosine of t plus some third constant. And I think this is a little bit what you were saying, Connor. In other words, I could think of this as, well, the same answer we just got a minute ago.
Oh, so are you just saying those are our constants?
Exactly.
Okay.
So it's actually plus an entire vector. Do you see what I'm saying? Like you're literally adding those points, kind of literally adding those individually to it.
Yeah, for some reason I was thinking the whole thing only got one constant. So I wasn't thinking about 3 separate constants.
So we wouldn't set then like the 2 natural log of t equal to 0 and all that other stuff. I mean, we wouldn't plug in 0 for those to figure out what our constants are. We
Yeah,
just.
you're exactly right. We're not quite done because
Oh, okay.
when was this true? At t equal to 0. Does that make sense?
Mhm.
So when t is 0, we need this thing to be 2. So we can actually figure out what these constants are. That's kind of the point here. In order to be at time 0, to have x be 2, so I do literally need to plug 0 into this. What's the natural log of 0? Maybe you find yourself going, I better get my calculator out.
That's 1, right?
It's 1. And so 2 times 1 is 2, which means that's already 2. So I could say that first one's actually 0 then, right? What about this one? When I throw in 0 for t here, I need 3. Well, 0 to the 4th is 0, which means C2 actually better be 3, right? What about this last one? I throw 0 in for t, cosine of 0 is actually 1, but that's -1. And so the only way I'm gonna get 5 then, since it's supposed to be 5, is -1 plus, well, 6. So without these initial conditions, in other words, without your initial position, if you didn't know that, without that initial condition, you would not be able to actually answer this question. Without knowing how much chlorine was in the pool when you started, just knowing the rate at which you were putting it in is not going to allow you to work backwards and figure out how much chlorine's in the pool. Now, if you said there was none in the pool, fine, that's an initial condition. At time 0, there was none. Then you can know, but you got to know what happened initially. And so the actual answer for this for S of t then, with those constants in it, is 2 natural log of t, and we're done. 2 natural log of t, and we found out C2 is actually 3, so it's 1/4 t cubed plus 3. And we found out that the constant 3 was actually 6, and so now that's actually the correct. So you can't know what those constants are unless you have an initial condition, unless that's somehow something that you know. You'll see a problem in your assignment where instead of giving you, excuse me, instead of giving you the equation, if you will, of the velocity in the middle, they're going to give you an equation for acceleration. And then you'll have to take the integral of that with an initial condition so that you can come up with the actual numerical values for v, not just c's in it. And then once you know that, then you'll have to do it one more time, take the integral again to get position. And so what's really cool about this in a larger sense is if you know an equation for position or acceleration or velocity, you can always use derivatives and integrals to figure out the ones you don't know. And we make a lot use of this in engineering classes that I'm teaching. So this is something that you want to have a good feel for. If you take physics, this is the main backbone of physics. You usually don't work, this complicated in 3D, if you will. But notice, I need to shut up. But like this is the one I want. Does that make sense? Because I can't graph the thing. I can't. This is what gave us the black curve that we started the class with, where you say, oh, okay, cool, look at the path it's on. Now that we know that, then we can say, okay, well, cool, how fast is it going and what's its acceleration? We now have a way to do that, but without the path, it kind of stinks. So going out the door just for the fun of it, I know we're overtime as usual, but let's just go see what that looks like, just because I made this up yesterday and I didn't.
I think I saw your DiffEQ class goes to 950. I think it's smart to give yourself some extra time.
It's because it's an 8-week class in the summer is the reason for that.
Oh, shoot. I forgot about that.
So it's not for extra time. It's because to get 5 credits, I think it is, in that short of time, we don't have a choice. But it actually works out better because just like today, we have the same discussions. It just always seems like there's kind of never time to make them happen. Let's see, vector. So graph. So what does this thing look like? It just seems like it might be fun, right? Because it has logarithm in it. It may not be. 1/4 t to the 4th. See, I wrote 3rd in the notes. I'll have to fix that.
It's showing your desktop, Doug.
Thank you. I'll just drag it over here. Save a little time. 1/4 t raised to the 4th. And then we said that was a plus 3. Finally, negative cosine t plus 6, or maybe it'd be nicer to write 6 minus the cosine of t. And so is this any fun? That's the kind of the question. Is this a neat path? Notice interestingly, it just populated it with 10 to negative 10 for some reason. So notice the kind of gut reaction is, well, no, that isn't very interesting. It's kind of it's realistic, I think, in the sense that this is just like somebody turning a corner, but it's sort of surprisingly dull, wouldn't you say? I'm finding myself thinking, where's cosine? Like, why is cosine not seeming to make any repetitive sort of contribution to this. Maybe it's microscopic somehow, I don't know. Anyway. So we say, okay, cool, I'm traveling along that path, and now we have got our velocity equation, so we can know the velocity at any point in time we want on there. Well, that velocity is a vector, and in this case, the magnitude of that velocity vector is the actual velocity. That would be the meters per second that you were actually traveling at, or whatever. But we're still a little bothered by the fact that that doesn't seem to be the same thing as the slope. So, oh, there is a little hint there that things get a little interesting. Notice when I kind of turn it sideways, is that starting to act like a sine wave? Notice how much you have to look at this to kind of see that. The main problem here is with t to the fourth in it. Does it make sense the y is blowing up super fast thanks to the t to the fourth? Because by the time I put in like a small number like 10, well, 10 to the fourth is thousands. And so I think that's part of the problem, part of why this is blowing up so big. I'm wondering if I would have to just set this time to go a lot further into the future before I would actually see. Maybe I'd see it from this view, but the problem is when I zoom out, I sort of can't really see it anymore. So
If you just did t to the second, would it completely change the graph? Or would it just shrink it up?
I think it would shrink it so that you might actually be able to see the cosine's contribution. I'm just guessing, but maybe I'd be able to, yeah. So I think the problem is you have to zoom out. I think that t to the fourth makes that cosine motion there just too subtle to see. Let's see what happens if I make it a 3. See how it just got kind of longer? Like I guess I can see now that it's still there, but it makes it really subtle. It's kind of like the amplitude of it is so low that I can't see it, and then I make it to the fourth and it's kind of even worse. But it's still kind of fun. I mean, even though it's still kind of an interesting world. Anyway, all right, as usual, stay after if you have questions. Otherwise, I will see you.
Thanks, Doug.
All right, thank you.
Thanks, Doug.
Thank you all.
So with that earlier function that we were working with, I took the second derivative of it, and I was wondering, because the y part turns into just a constant 1/2. So I was wondering if that was significant in any way.
Yeah, keep in mind what that is doing you is telling you the change of the change. So in a sense, if we think of the derivative as telling us kind of the slope of the graph, then the second derivative is telling you how the slope is changing. And so you're saying you took the derivative and got 1/2 for the y. Well, that basically means from now on, no matter, that's just telling you the y coordinate of the slope is changing by 1/2. And that doesn't change, like it kind of doesn't matter where you are now, but the y part of the slope will be changing by 1/2 forever. So it's telling you how the slope is changing. Anytime you take a derivative, it's telling you how whatever you just took the derivative of, it's just telling you how it's changing. So in that case, it's just slope. But yeah, it's kind of hard to kind of conceptualize or visualize, right?
Yeah. So
Hurts my brain too.
So our vector, if we were to say that was the velocity, then the second derivative, that's just the acceleration.
Yeah, I mean, that's why velocity acceleration, but in this case, it's because this problem, if you weren't thinking of it as a position, velocity, and acceleration, then it'd be position, slope, and change of slope.
Okay. Yeah, that makes sense.
Let me go in here and try typing that in really quick just for the fun of it and see what it does. So derivative of cosine is negative sine Y value would be 1/2 permanently. Derivative of sine is cosine, so that'd be -4 cosine of 2a. So if I said, let's make that vector go from A to A plus U. So then that's telling us how the slope is changing with whatever point we happen to be at. I'm not sure why I lost that vector. Somehow that other vector I had just disappeared, but looks like I sort of lost my ability to animate that somehow. It's like A is not. I was wanting to animate it, but. So it's hard to conceptualize what that's telling you, but it's basically telling you how the vector is changing from there. I think it's because I just typed the. Oh, that's because I used A again. No, that's right. So I'm staring at those two vectors. This one is telling us about the slope, and this one up here is telling us how the slope is changing at that point. So it's, and again, that's very hard to visualize, right? But it's basically saying, well, the Z coordinate is getting bigger, right? Because it's pointing up. So it's saying your Z coordinate is going to get bigger. And then if I look at it in this direction, notice it's saying the Y coordinate's also going to get bigger because see how it's pointing to the right where the positive Y is. And then if I look at X, it's like, oh, it's backwards in X. So the X coordinate's going to get smaller. The Y coordinate's going to get bigger, but not bigger very much. Notice it isn't very much Y, but it's really big Z. So it's saying your Z coordinate's going to get bigger faster than the rest of them. The Y coordinate's going to get a little bigger, and the Z and the X coordinate's going to get a little smaller. That makes sense?
Yeah, I can see that.
Yeah, and it's of the slope. That's how the slope is going to change, not the coordinate itself. It's how the slope is going to change if I move to the next spot. So it'd be kind of cool to look at the slope right now and notice the slope right now is 0.54, 0.5, and -1.82. And so then if I went from 1 to, you have to memorize that, 0.54, 0.5, and -1.82. So then if I went to 1.1, did you see X got smaller
Yeah,
and Y got a little bigger and Z got a little bigger, but no, it was negative. So don't be confused by that. It went smaller negative, so it got bigger. So do you see how we saw that happen? That's
Yeah.
what a second derivative is telling you. It's how the slope is going to change. So that's kind of cool.
okay. That answers my question. Thank you.
That's a wonderful question.
Have a good weekend.
Thank you. You as well.
So I had a quick question about like that math class that you said would transfer over to OIT. What class was that?
At OIT or here?
Oh, here, that you're teaching in the
It's
summer. What class?
It's 256. I'm gonna see if I can find out.
Because I'm pretty sure I'm going to be going to OIT and I'm wanting to get as many credits here as I can before I transfer.
Yeah. Here we go, right here. RCC, Oregon Tech course equivalencies. Select your institution, Rogue Community College. Where are you? Choose subject. Subject 0. Math. Math 256. Submit. 321. So you take 256 with us. So you might go on OAT's site and kind of, maybe you don't exactly know what you're going to do over there, but basically if you take that with us, you'll have 321 equivalent over there. And that could just be random credits, or it could be specific to the program that you're actually taking, but.
Okay.
Notice they have a little side note because 100 and 200 level classes are considered lower division, 300 and 400 are considered upper division. So because it came from us as a 200 class, even though it transfers for 321 and you get credit for it, they're saying we're not giving you any upper division credit for it. So that won't matter if you need the class, because you'll have 321 and your requirement is met. But if it's like you need, 20 classes that are upper division, then they'll say, well, sorry, 256 doesn't count as one, even though they credit as 321. So it's kind of funny actually, because it's because we're, a low life community college. And I sort of get that, but it's sort of funny that we teach the same thing they teach and they give 321 credit for it. It does kind of put them in an awkward place. Anyway, now you know.
Awesome. Thanks. Yeah, I'm gonna try and contact OIT and just try and figure out like classes and everything, because I'm looking at the degree requirements for an applied mathematics of a bachelor's degree, and they're like you only need 18 lower division required courses, and then you need 44 upper division core requirements. So
yeah, feel free to call somebody over there. It depends on what you end up doing with it. You're talking about teaching, right?
yeah.
If you can do it this summer, you should take it. In my case, I taught math for 20 years and I'd never taken differential equations before. And granted, I was teaching a lot of that at high school, and calculus 1 and 2 were the highest thing we taught. And so I didn't have much occasion to, but it's so deep in my understanding of like what math can do. And I have some applications that I made up projects for in that class. One of them, my favorite one is how, let's do this with a piece of paper, but if you have a beam in the real world and you put weight on it, it kind of does that. It sort of bows down, deflects down. And there's this algebra equation that tells you how much that's going to deflect down based on a few factors, like how long is the beam, and then how, this is made out of paper, so it's pretty wimpy. So what kind of material is it made out of? And so there's this really neat algebra formula that's super simple algebra formula. I actually show Math 60 students, Algebra 1 students, I show them that formula just because it helps them understand like what a formula can do in a practical sense. But it's actually differential equations that makes that formula for us. Like that's where that formula came from. So the richness of kind of understanding where some of the formulas that we have come from. And I've said that a little bit in my calculus classes, but I didn't have you for Calc 1 and 2, but most of calculus is not so much like you're going to leave class and then go have to do some calculus. Calculus actually produces algebra formulas that get used just as algebra formulas. And so, one argument is like, well, great, some nerd made it and now I can use it and build my house. I got no problem with that. Great. But for me, because I like math and teach it, and maybe that's going to be you too, to have a sense of like, yeah, but I can make that formula for myself. That's a cool confidence, and as a math teacher, that's part of what you're trying to impart to people is the ability to speak the language. But I design houses on the side, and so when I'm sticking a beam into a house, just that sense that I really deeply understand kind of the forces that are acting on that beam, and I like that feeling. It actually doesn't have anything to do. Honestly, I can't really do my job any better as a result of that. But the richness of a sense of understanding feels really good to me. I really enjoy that sense. So to have been allowed to be a math teacher without somebody making me take that class just seems like a shame. But one thing that bothers me a little bit, you've seen my teaching style for a few months now, but I really like applications because I think that's what allows people to hang on to stuff. It's not that you have to learn math to go use it. You can just love math and think it's beautiful and never want to use it. That's fine. But I know differential equations is taught really poorly in terms of applications by most people. It's taught really sterile at state university level, and I probably would have hated it and learned nothing is kind of my guess is, frankly. So I don't know. I think it's partially because I think students learn better that way when they have some applications to hang on to. But I need them. Like I can't even make sense of anything unless I have some physical model of it and some way to get my hands on it and some kind of a project or something. Otherwise it just doesn't sink in.
Yeah, that definitely makes sense.
Yeah, well, enjoy having you in class. I hope you can find a reason to take it because I think you'll like it.
Yeah, I'll definitely give them a call and see. I might just sign up for it and just be like, hey, it's cheaper over here. And I
Yeah.
like you as a teacher. You like the other teacher I had, she made us memorize like a lot of formulas. And like she would spend like the first 30 minutes of class like showing how the formula was made, but I just didn't really get it. And then she's like, okay, here it is, just memorize it. So
Mhm. Yeah, it's fun when you can touch it and so forth. It's always awesome. Yeah, well, sign up for it.
okay.
And drop it. Like if it doesn't work out for whatever reason, just drop it. It's no big deal. You can drop it. First couple weeks of class and doesn't matter. So yeah. All right. Cool.
Thank you. Have a great weekend.
You too. See you on Monday.
See you.